Good evening, students. I hope all of you are following my lectures very seriously. Our today's topic is Heisenberg's uncertainty principle, one of the most important principles in physics. Okay, right? This has changed the way people look at physics and the way physics has to look at the universe. Okay, till then, right? Physics was an exact science. People thought that they can predict things as accurately as possible, but this uncertainty principle said it is impossible to find, right, some things accurately. Means if you want any one thing to be very accurate, you have to compromise on some other property. This was nearly unexpected and unbelievable principle in those days. And this principle, though it is apparently negative looking, right, it is one of the most fundamental principles, as fundamental as conservation of energy or conservation of linear momentum or conservation of angular momentum. Okay, right? The principle says what? The product of the uncertainties in the variables of canonically conjugate pairs whose operators are Hermitian can never be less than h bar by 2. Okay, right? The normal statement will be like this in plus 2 level or in BSc level. Okay, the uncertainty principle definition will be, right, it is impossible to find the position and momentum of particles simultaneously accurately. Okay, that is, a particle is moving along x-axis like this, it is having some mass, it is moving some velocity v such that its momentum p is there. Okay, at any instant its position is x, say. Okay, what does that, what is the uncertainty principle general statement? It is impossible to find the position and momentum of a particle accurately at the same instant. Okay, right? Means if you want to find momentum accurately, you'll have to forego its accuracy of position. If you want to find out its position accurately, you have to forego its momentum accuracy. Okay, right? It is like this. The statement initially appears that you cannot find the position and momentum simultaneously accurately means both things I cannot find simultaneously accurately, but one thing I may find. That's the impression actually that statement gives, but actually it is not like that. You cannot find either position or momentum, right, most accurately. There will be some inherent uncertainty in that. Okay, that is actual statement. Okay, right? So we write, what is uncertainty in position? Uncertainty in position is delta f. X is position, its uncertainty means error in finding out its position is written as delta x. If p is momentum, uncertainty means error in momentum, right? Finding momentum is delta p. Okay, delta px, I write, is greater than or equal to, can never be less than h bar by 2 means greater than or equal to h bar by 2. This is a statement actually. Okay, right? Delta x into delta p is greater than or equal to h bar by 2. Most of you might have heard this statement also in plus 2 level, right? In second year it comes. Okay, right? The statement actually, right, goes like this. The statement actually goes like this. The product of the uncertainties in the variables of canonically conjugate pairs. Okay, we'll see what are canonical conjugate pairs once I go into quantum mechanics. Okay, right, whose operators are Hermitian. Whose operators are Hermitian. Again, what are Hermitian operators also will be clear by definition once I enter into quantum mechanics. Hermitian operators means, right, those operators whose eigenvalues are always real. Okay, all physically observable quantities operators in quantum mechanics must be Hermitian operators only, because the eigenvalues of Hermitian matrix is always real. They are always real. Okay, so when I want to find out position or a momentum or energy, I cannot have imaginary eigenvalues. Okay, eigenvalues should always be real. So the product of the uncertainties, the variables of canonically conjugate pairs whose operators are Hermitian can never be less than h bar by 2. Means the product of the uncertainties, right, the product cannot be less than h bar by 2 means, right, it can be greater than or equal to h bar by 2. What is h bar? H by 2 pi. So h bar by 2 means it is like greater than or equal to h by 4 pi also we can write. Means it can have, right, minimum value is h bar by 2. Anything above h bar by 2 is acceptable according to uncertainty principle. Now, what are those canonically conjugate pairs? What are those canonically conjugate pairs means, right, it is like this. Uncertainty principle is not only related with x and px, but the canonically conjugate pairs are x comma px, I will write. Okay, y comma py, right, z comma pz, right, energy comma time, and angle comma angular momentum J. Angle comma angular momentum. These 5 pairs are canonically conjugate pairs. The uncertainties in the variables. What are the variables in the first canonically conjugate pair? Position x and its component, x component of momentum px. Uncertainties in the variables of canonically conjugate pairs. Uncertainty in x, I'll write it as delta x. Uncertainty in px, I'll write it as delta px. The product of delta x and delta px cannot be less than h bar by 2. Okay, means cannot be greater than, cannot be less than h bar by 2 means can be greater than or equal to h bar by 2. So when I expand this uncertainty principle statement, I'll get something like this. Okay, right? Delta x into delta px. Delta x into delta px greater than or equal to h bar by 2. Right? The second pair is delta y into delta py. Right? Delta x into delta py greater than or equal to h bar by 2. Okay. Next, delta z into delta pz greater than or equal to h bar by 2. Okay, delta E into delta T, uncertainty in energy, uncertainty in time, greater than or equal to h bar by 2, delta theta and delta J greater than or equal to h bar by 2. This is how we fully expand uncertainty principle. Uncertainty principle is applicable for these products in those pairs only. Okay, means you cannot find the x position and you cannot find the x component of momentum simultaneously accurately. Okay, right? One, that is, they can never be less than h bar by 2. What is the minimum value of uncertainty? Right, equal to h bar by 2. Now what is the meaning of this uncertainty? Okay, x is the position, right? A particle is moving like this at any instant, right? Right, when the particle is moving with speeds comparable to velocity of light, right, I cannot tell the particle whether it is exactly at x or x plus dx. Suppose I'll say the particle can be anywhere in a short range x to x plus dx. The uncertainty in the position of the particle becomes delta x. Okay, similarly, particle's momentum is p. If I measure its velocity, suppose its velocity is anywhere from v to v plus dv, such that its momentum will be anywhere from p to p plus dp. So what is the uncertainty in momentum? dp. That uncertainty in momentum dp or delta p, uncertainty in position delta x, that their product cannot be less than h bar by 2. Means greater than h bar by 2, greater than or equal to h bar by 2 we say. Okay, now what is this uncertainty? What is this uncertainty mean? Suppose say, means our inability of finding the thing very accurately. Okay, now say what is my height if I ask you, right? If I am fully visible, right, and if you are experienced LIC agent or you are a tailor or something like that, you will say, sir, you are around 5 feet 10 inches. Okay, are you very sure about my height that I am exactly 5 feet 10 inches? An experienced person will say anywhere 1 inch plus or minus 1 inch. Okay, means your height will be anywhere like 5 feet 10 inches plus or minus 1 inch, they say. Okay, so my height will be 5 feet 10 inches plus or minus 1 inch. Okay, means my height can be anywhere from 5 feet 9 inches to 5 feet 11 inches as accurately as possible. An experienced person will be able to tell, say. Or what is the length of this pen? Can we, by looking at it, can we tell exactly it is 7.9 centimeters? No, I will say its length is anywhere from around 10 centimeters plus or minus 1 centimeter, I will say, as close as possible. Okay, so I'll write this, the length of the pen as 10 centimeters. Okay, uncertainty in the length of the pen is 1 centimeter plus or minus 1 centimeter. Okay, this is known as uncertainty in the length of the pen delta L. Why? Because there is no measuring instrument. If I give you a scale, you will be able to find out the length. Sir, you will say, suppose say it is around 10 centimeters, right, and 2 millimeters. Suppose the length of the pen is, the tip of the pen goes and stops somewhere between 10.2 millimeters and 10.3 millimeters. Okay, so you know that it is more than 10.2, but it's less than 10.3. Okay, the tip of the pen is stopping somewhere over there. Means what do you say now? Right, the length of the pen is more than 10.2 millimeters and but less than 10.3 millimeters. Means how do you write that? Okay, 10 centimeters. Okay, 10.2 centimeters to 5 you will write plus or minus 0.05. Plus or minus 0.05, that is, its length is somewhere between 10.2 millimeters to 10.3 millimeters. Okay, right? Means that 0.05 is the uncertainty in finding the length of the pen. Okay, right? Why am I getting that uncertainty? Because the minimum, the least count of my scale is only 1 millimeter. Anything less than 1 millimeter normal scales cannot measure. If I give you a vernier calipers can accurately give up to 1/10 of a millimeter also. Suppose the tip of the pen when you observe it in a microscope goes between 10.21 and 10.21 to 2 millimeters. Again, even vernier calipers is useless. Only thing is the uncertainty is decreasing, that's all. The more accurate instrument, more efficient instrument you use, screw gauge if you use, it can measure up to 1/100th of a millimeter. But if suppose at 1/100th of a millimeter at microscopic level, suppose the pen goes between 10.235 and 10.236, even screw gauge becomes useless. Okay, there will be some uncertainty. Means the more efficient, the more accurate instruments you use, the lesser will be the uncertainty. By just looking at it with our naked eye, right, my error will be about plus or minus 1 centimeter. If I use a scale, it is plus or minus 1 millimeter. If I use a vernier caliper, plus or minus 0.1 millimeters. Like that, the accuracy increases, right? As the accuracy increases, uncertainty keeps on decreasing. Okay, but the uncertainty principle, the position, or what you call the uncertainty in position or momentum, is not because of the inefficiency of the instruments. Okay, it is the inherent property of nature itself. Okay, suppose I want to find out an electron is moving, I want to see where that electron is. In order to see that electron, I have to send some radiation towards it. That radiation should get reflected and enter into my eyes. Okay, some radiation should get reflected from electron, means theory says what, scattering theory says what, the size of the particle should be more than the wavelength of the incident radiation. Electron size is extremely small, or atom size is extremely small. I have to use not even X-rays, I have to use gamma rays. When a gamma ray photon goes and strikes the atom, okay, that atom or electron will not exist there, it will get disturbed. By the time the photon reaches my eyes or into the microscope or whatever microscope, okay, right, electron is no longer there. You have disturbed its momentum, you have disturbed its position also. Okay, means the very nature of trying to find out, okay, the position or momentum will disturb the system. Okay, it is inherent in nature, nothing to do with the efficiency of the instrument, however efficient our instrument is. Okay, the very process of measurement will disturb the system. Okay, that is the uncertainty principle. Inherently there will be some uncertainty in the finding out the position. There will be some uncertainty in finding out the linear momentum of the particle. And remember, this principle is applicable only for if the particle has x motion, it is uncertainty in the position along x-axis multiplied by uncertainty in the x component of momentum only, not other components of momentum. Okay, right? So it is like this: 5 feet 10 inches to 1 inch plus or minus. This plus or minus 1 inch is the uncertainty delta h in my height. Okay, plus or minus 1 centimeter uncertainty in measuring the length of the pen. Okay, it depends on the instruments we use, but still there will be some uncertainty left out. And one more thing, remember, whatever is uncertainty, what is my height means, you will say 5 feet plus or minus 1 feet. To some extent it is acceptable. Okay, 5 feet plus or minus 1 feet. My height can be anywhere from 4 feet to 6 feet. Acceptable only, because I will be like that. Okay, but if you say, sir, your height is 5 feet plus or minus 5 feet. Okay, is it wrong? No. Okay, because my height will be anywhere from 0 feet to 10 feet, right? Any man will be between 0 feet to 10 feet only, isn't it? Means that answer, though it is technically correct, it is not a logical answer, isn't it? If you ask somebody what is the time now, he says anywhere in the any time from morning to evening. You do expect such an answer? No, you want some reasonable answer. Okay, if the other fellow says I don't have a watch, it's around 12:30, 12:45, 12:30 to 1, that is acceptable. Half an hour error without watch, he is telling like that. If you know sometime in the morning, if he says, right, it is an irritating answer. Similarly, if somebody says what is my height means, sir, it is 5 feet plus or minus 5 feet means, right, if some L is there, uncertainty, right, plus or minus delta L that delta L cannot be equal to L. Okay, though it is technically correct. What is the length of this pen? 5 centimeters plus or minus 5 centimeters. Means its length is anywhere from 0 to 10 centimeters only. It will be definitely like the technically correct answer only. But do we expect such an answer? No. Okay. What about the other one? So what is the length of this pen? Means, sir, it is 5 centimeters plus or minus 10 centimeters. Okay, means what? Its length can be anywhere from minus 5 centimeters to 15 centimeters. It is a meaningless answer. Means the uncertainty delta L cannot be greater than L. Okay, nobody will say what is my height. Means your height is anywhere from 5 feet plus or minus 10 feet. That is meaningless answer it is. So delta L becoming greater than L is meaningless, ruled out totally. Delta L equal to L, though it is technically correct, still an irritating answer. Still an irritating answer. Okay, you want some meaningful, reasonable answer, isn't it? Right? Somebody, suppose say you got some marks, somebody, your parents ask you how many marks you got in the paper. I got some marks from 0 to 100. If you say, what does it mean? Anybody gets 0 to 100 only, isn't it? Okay, say around 55 I got, okay, acceptable. Around 75 I got, okay, acceptable. Okay, so at 10 marks plus or minus, how many marks do you get? 70 plus or minus 5 marks. It is reasonable answer. Okay, but I will get anywhere from 0 to 100 in the paper. Means everybody gets like that only. The way, imagine the way other fellows look at you if you give such an answer. Okay, right? So L plus or minus delta L means uncertainty, right? Whatever is that parameter, its uncertainty cannot be equal to that also. Okay, so what does that mean? Delta L must be less than L only. Whatever is uncertainty, that should be less than the actual value. Okay, it cannot be equal to, it becomes meaningless. It cannot be greater than, it is ridiculous. Okay, right? So remember, whatever is uncertainty, delta X must be less than position X only. Similarly, delta Px must be less than Px. Okay, right? If linear momentum is 10, what is uncertain in linear momentum? It cannot be 10. Okay, it should be less than 10 only. It can be 5 or 2 or 3. The smaller the value, the better it is. Means the more accurate your experiment is. Okay, so remember, right, position and momentum uncertainty should be less than, value should be less than the actual values of position and momentum. By chance, if I take delta L equal to L, what does that mean? Am I taking the best answer or worst answer? I am taking the worst result. If delta X equal to L, delta L equal to L, if I take, means I am accepting the worst value for L, uncertainty L. That is, what is my height? 5 feet plus or minus 5 feet. Okay, means my height can be anywhere from 0 to 10 feet. Though it is correct, it is the worst possible answer you can expect. Okay, that is a maximum value of 5 you can take. Okay, maximum value of uncertainty in my height can be 5 feet. Usually, uncertainty must be less than the actual value. Okay, right? In solving problems, keep that in mind. Okay, I'll come to this factor. Why I am stressing this point means, okay, in the successes of what you call uncertainty principle, right? It has proved beyond doubt that it is impossible for the electron to stay inside the nucleus. Okay, there we take the uncertainty in momentum. The momentum value itself is equal to uncertain moment. That's the worst value we take. Even if I take the lowest value, right, I'll get a meaningless result, which proves that it is impossible for the electron to stay inside the nucleus. If it cannot stay inside the nucleus, it must be outside the nucleus only. Rutherford's model got perfected by that. Okay, right? One confirmation that it is impossible for the electron to stay inside the nucleus. That is what our uncertainty principle has established in the earliest days. Okay, so uncertainty principle, there are 5 equations here. Delta X into delta Px. Remember, uncertainty principle is applicable only for the variables of these pairs only. You cannot interchange the variables in pairs. Okay, you cannot take X and Y. You cannot take X and Py. You cannot take Y and Px. Like that you cannot take. You should not interchange the variables in pairs. If you interchange the variables in pairs, uncertainty principle is not applicable. Uncertainty principle is applicable only for the variables of these canonically conjugate pairs. X Px, Y Py, Z Pz only. Okay, by chance, if somebody says what is delta X into delta Py, delta X into delta Py, right? X is in one pair, Py is in another pair. Delta X into delta Py, uncertainty principle is not applicable. So the answer should be equal to 0. Okay, this is one previous MSc entrance question. Okay, right? The uncertainty, according to the uncertainty principle, delta x into delta py equal to somewhat he has asked greater than or equal to h bar by 2, equal to h bar by 2, equal to 1, equal to 0, like that. Okay, because the variables are interchanged here, right? Delta x into delta py equal to 0. What does that mean? You can find out the x component of position and y component of momentum accurately simultaneously, no objection for anybody. Okay, you cannot find the x component of the position and x component of momentum only, right, simultaneously accurately. It does not even mean, right, that you can find one thing accurately. What happens if I can find one thing accurately, right? It will be like this. Suppose say somebody says, sir, I have found the momentum of the particle with 100% accuracy, there is no uncertainty at all. Okay, what does that mean? For him, delta px is equal to 0. Then what will happen to answer according to uncertainty principle? Delta x into delta px must be greater than or equal to h bar by 2. So delta x equal to, or delta x greater than or equal to h bar by 2 into delta px, I'll write. Okay, now you are saying that you have found the momentum most accurately, uncertainty is impossible, delta px equal to 0, you said. Put delta px equal to 0 here. What will happen? Delta x becomes infinity. Okay, uncertainty in the position itself is infinity, means position becomes infinity. I told you uncertainty in length is delta L, means what is the minimum value of the length? Delta L only. Delta L can be anywhere more than delta L. Okay, but L can be more than delta L, but it cannot be less than delta L. What is the worst value of L? It is equal to delta L. Okay, if somebody says the uncertainty in my height is 1 feet, okay, it can be 4 feet plus or minus 1 feet, or 5 feet plus or minus 1 feet, or 6 feet plus or minus 1 feet. Okay, no problem. But can it be 1 feet plus or minus 1 feet? Impossible. It cannot be less than 1 feet. Means if uncertainty itself is 1 feet, what should be the height? Minimum value, worst and worst value must be equal to 1 feet only. That itself is not actually acceptable, but still, that is the minimum value. So, uncertainty in position itself is infinity, means, right, position must be infinity. Infinite position means particle can be found anywhere. Okay, I don't know the position of the particle at all, which is not possible. Okay, so delta px cannot be equal to 0. Similarly, you put that delta x to this side, okay, and change this one. Okay, suppose you have found the position most accurately. Delta x equal to 0, if you say, what about delta px? Delta px will be h bar by 2 into delta x. If delta x is equal to 0, delta px becomes infinity. When delta px itself becomes infinity, what is the value of the momentum? Momentum must also be infinity. No particle can have infinite momentum. Impossible, isn't it? Means you cannot even find one thing accurately in that pair. Okay, only thing is you can make it smaller and smaller, that's all. The more, the smaller the uncertainty in one value, the higher will be the uncertainty in the other value. Means if you want to find out position as accurately as possible, you can decrease delta x value, that's all. You cannot make it 0. If you try to make it 0, momentum becomes infinity. Impossible. No particle can have infinite momentum. Okay, right? Similarly, only thing is what? You can make this delta x as small as possible, but at what cost? As delta x becomes smaller and smaller, delta px, uncertainty in momentum, becomes higher and higher. Means momentum value itself will become higher and higher, meaningless also. Okay, so only thing is, means whatever it is, according to uncertainty principle, it is not possible to find the position of the particle and that component of momentum simultaneously accurately. If you want to compromise, if you want to find out one thing accurately, as accurately as possible with the minimum error, the uncertainty in the other parameter will keep on increasing. This is putting a limit on the what you call man. Okay, how far I can, to what extent I can go in the universe, means there are inherently certain limitations for human beings, or nature itself is putting those limitations on man. Okay, you cannot find certain things accurately. There is always some inbound, right, error in finding, or uncertainty in finding. Okay, right? So it's a very important principle, far-reaching consequences in physics, not only in physics. Okay, what you call metaphysics also, just like relativity. Einstein's theory of relativity has what you call repercussions not only in physics, in all other branches of science, and apart from science, in some metaphysics also. It has brought so many changes. Okay, in the way people think about the universe, the time, okay, the dimensions, right, have changed. One uncertainty principle, and what you call the de Broglie concept, material particles behaving like waves, okay, and quantum theory, waves behaving like particles. These are all right trend changing, right, things in physics. That's why these have come under what is known as modern physics in those days. Okay, all modern ideas, and which were not there conventionally. All these things are impossible. Conventionally, all these things are impossible. Why do we study physics? Means what do we say, man? Okay, because it is there in the syllabus, sir. Okay, apart from that, actually, what is the purpose of studying physics? If I know anything about now accurately, I will be able to predict the future. I should be able to tell its past also. Suppose, say, a car is moving in front of me now. Okay, its initial velocity u equal to, suppose, say 5 meters per second. Its acceleration a equal to 2 meters per second square. It is in front of me now, right? It is like this, and it is going in this direction, right? Now while sitting here, I want to find the position of the car after half an hour. Okay, where do I find the car after half an hour? Somebody asked me. I don't have to run behind the car for half an hour and see where it is and come back running with gasping and saying, sir, car is in somewhere after half an hour. No, I need not. I'll simply sit in my place only. I'll use the formula S equal to ut plus half at square. Okay, I know the initial velocity, I know the acceleration. After half an hour means I'll put t equal to half an hour. Okay, I'll find out what distance the car goes. Okay, car will travel a distance of say 25-30 meters, means from my Hyderabad, car is somewhere around some Bhonegir or so, 50 kilometers, something like that. Okay, means I'll tell after half an hour the car will be found in Bhonegir. I can tell confidently like that, sitting here, okay, not going there. What happens after half an hour, I am able to tell. Similarly, where was the car 10 minutes behind me? Okay, I'll simply substitute t equal to minus 10 seconds and see car is somewhere at this position 10 minutes before. Means what does that mean? Right, if I know about the system perfectly now, I am able to predict the future of the particle. I am able to tell the past of the particle also. That is the pride of physics. Okay, physics feels that if I know anything about the system correctly now, I'll tell the future, I'll tell the past also. That's how people are able to tell how when eclipses occur. Okay, some after so and so people are able to tell, right, sun, moon will be closest, the biggest moon of the year. There again this combination happens after 35 years. We are able to tell how all these things because of calculations only. I know the present system of all the planets. Okay, I will be able to tell after 15 years which planet will be there. Okay, what happens after 15 minutes, or how long back such combinations occurred. People are going back and says 500 after 500 years again this combination of 4 planets in same position is something like that. How people are able to tell? Because of formula like this, calculations. Okay, means that's the pride of the physics. Okay, physics says what? If you know about the system of the particle now, you can tell its future, you can tell its past. Okay, that is the greatness of physics. But this Heisenberg's uncertainty principle, right, has come and given a wild stroke, okay, to physics, that forget about predicting the past and predicting the future of the particle. It is impossible for you to find the system's state accurately now itself. However accurate your experimental setup is, you cannot find out its position, right, without any error. You cannot find out its linear momentum accurately. When you cannot find out the system's properties now, how accurately you can predict about the future and how accurately you can predict about its past? Not possible, isn't it? It's a blow to the physics actually in those days. Okay, right? Physics thinks that I can tell everything, but uncertainty principle said forget about future, forget about the past. You cannot even measure the present state of the system accurately. Inherently there will be some uncertainty, some errors in the measurements. That is the limitation imposed by the nature on man. Okay, right? That is how it has some consequences in other branches of thinking also, okay, apart from physics. Now let us come back to our physics part, right? So delta x into delta px is greater than greater than or equal to h bar by 2. Okay, right? Now I'll write, we know that according to de Broglie concept, P equal to linear moment of particle equal to h by lambda, sorry. Okay, I'll multiply with 2 pi and divide it with 2 pi. Okay, h by 2 pi is nothing but h bar. Okay, lambda by 2 pi, 2 pi by lambda, I'll take it as k. Okay, such that 2 pi by lambda is k, so I can write P equal to h bar k. Okay, now delta P, h bar is a constant. So what is delta P equal to? Delta P equal to h bar into delta k. Okay, now substitute this value in this equation. It is delta x into h bar into delta k greater than or equal to h bar by 2. This h bar gets cancelled. The other form of uncertainty principle is delta x into delta kx, right? Is greater than or equal to half. This is how we can write. This is another form of uncertainty principle. Okay, where k is propagation constant, k equal to 2 pi by lambda, where lambda is its de Broglie wavelength. Okay, right? Now next one, we have the energy time uncertainty is what? Energy and time delta E into delta T greater than or equal to h bar by 2. But according to quantum theory, what is E equal to? E equal to h bar omega. That is Max Planck quantum theory. Okay, so delta E, you can take it as what? H bar into delta omega, because h bar is anyway constant. Okay, delta omega. Now substitute this value in this equation. What do you get? Okay, what do you get? Right, h bar into delta omega into delta t greater than or equal to h bar by 2. H bar gets cancelled. The other form of uncertainty principle is delta omega into delta t greater than or equal to half. We can write greater than or equal to half. Okay, right? So these are different forms of what you call uncertainty principle, right? Apart from delta x, delta px, remember you cannot change the variables in the pairs. Okay, x and px is one pair, y and py is another pair, energy and time is another pair. Okay, you cannot find the energy of the particle and it's the time, right, accurately, but you can find energy and momentum. If in the examination, what is delta p into delta e? Okay, energy and momentum can be found very accurately simultaneously. Okay, right? Because we are, once I go into quantum mechanics and commutation operators, okay, commutation operators, we say that, right, energy, if you are finding energy means you are getting accurately, momentum will be found accurately. If you can find the momentum accurately, you will find energy accurately. There is no uncertainty principle here. So delta p into delta e, you can take it as 0. Okay, if you change the variables in the pairs, uncertainty principle is not applicable. You can write it as equal to 0. Only uncertainty principle is applicable only for the variables in those pairs. What are the pairs? What the pairs are, what we have seen: x comma px, y comma py, z comma pz, and right, energy comma time, and theta comma angular momentum. Okay, angle comma angular momentum, position comma linear momentum, and energy and time. Right, delta E into delta P. Okay, delta E into delta P can be found accurately. Uncertainty principle, delta E into delta P will be equal to 0. Okay, now what is the most RMS, what you call root mean square value? I'll take this because there is some error. What do we do in the experiment? When you are doing some experiment in the lab, you will not simply take one measurement and come out. Okay, right? Because you are bound to get some error. What are you in the lab? What you will be doing? You will take some 5 or 10 readings. Okay, slightly variable, slightly different readings will come. Okay, even though you are doing the experiment as cautiously as possible, every time you won't get the same result, there will be slight error. So you will take the standard deviation. Okay, right? You will try to arrive at the most probable value. Okay, root mean square value we call. Okay, how do we find out the root mean square value of x? Means it is like this. Okay, delta x, the RMS value of the uncertainty in the position, can be written like this. Okay, delta x is uncertainty in position. What is the standard deviation of that error or of the uncertainty? RMS value of the uncertainty is, right, x square, average value of x square. Okay, you will first measure the position. You are bound to get some error, so you will square and you will take the average value minus x expectation value whole square. This is known as mean square error, right? If you put square root here, x square expectation value minus x expectation value whole square. Okay, that is average value of x square minus average value of square of the average value of x under root is known as root mean square value. Similarly, delta px, right, RMS value will be like this, right, px square of the expectation, sorry, px square, it is like this. Okay, minus px whole square under root. These are the RMS values of uncertainties in position delta x and RMS value of uncertainty in the momentum delta p. Okay, the product of these two uncertainties RMS values cannot be less than h bar by 2, means greater than or equal to h bar by 2. Okay, sometimes some questions appear like this. Okay, in the examination, the product of the RMS values of uncertainties in the position and momentum of a particle, that is the question. Okay, 4 options will give you, can have any value from 0 to infinity, that's the first option. Okay, can have only a unique value, a single value they can have. Okay, that the product can have a single value, that is second option. Third one, can have all possible values up to a certain maximum, means there is some maximum value, this product can have all possible values below that maximum value. And the fourth option is can have all possible values above a minimum value. Okay, which options are correct? Theoretical question. This has appeared once in GATE physics exam. Okay, the RMS values of the uncertainties in the position and momentum of a particle can have any value from 0 to infinity. First option, no. Okay, it cannot have any value from 0 to infinity, right? Can have only a single unique value. No, it can have any value, right? The product should always be this much. No, uncertainty principle is not saying like that. Can have, what do they have? There is one minimum value. What is that minimum value? H bar by 2. And above that H bar by 2, it can have any value greater than or equal to, means they have a specific minimum value H bar by 2, and above that H bar by 2, that product can have any value. It can be H bar, it can be 2H bar, it can be H or H square or 100H also. Uncertainty principle has no objection. It only says their product can never be less than H bar by 2. There means there is one specific value H bar by 2, but the product can have any value that H bar by 2 and all values above H bar by 2. Okay, so this is one point which you should keep when you are appearing for any exam. Okay, right now, so what is the meaning of uncertainty? Again, I'll come back. I told you what is the meaning of uncertainty in my height, means how accurately you can tell with what inaccuracy, right? 6 feet plus or minus 2 inches, 6 feet plus or minus 1 inch, that plus or minus 1 inch plus or minus 2 inches is the uncertainty in the position. Now I am standing in the studio room. Okay, people outside, they cannot see me, right? They only know that I am inside the room. What is the accuracy with which they can find me, my position? All that they can say is this fellow is inside the studio room only. But inside the studio room, I can be anywhere from that end of the wall to this end of the wall. Okay, I may stand there, I may stand here, I may stand here, or I may go to that side also. So what is my limitation? I can stay anywhere between these two walls. Okay, they don't know that. People who cannot see me from outside, they cannot tell. All that they can tell is what? This person is inside the room, but where exactly I'm standing inside the room, no, they will not be able to tell. So the width of the room becomes the uncertainty in my position. Width of the room becomes the uncertainty in my position. What is the maximum uncertainty in my position? I cannot penetrate through these walls and go outside the walls, isn't it? So all that I can do is what? I'll be inside this room only. So maximum uncertainty possible for my position is the width of the room is the maximum uncertainty. Uncertainties cannot be more than the size of this room, isn't it? Right? Similarly, some questions come, right? Two particles, one electron and proton, right? Electron is negative proton, right? Are present in a one-dimensional box, infinite one-dimensional box of length L. Okay, right? And so uncertainty in the momentum, or what you call the two particles are present inside a one-dimensional box. They cannot escape the box outside. But only thing is that I don't know whether electron is here or here or here or here. I don't know. Similarly, proton also can be anywhere from this end of the wall to this end of the wall. I don't know where it will be because I cannot see inside. So what is the maximum uncertainty in their position? Right? Delta x equal to maximum uncertainty in their position. Delta x is equal to the length of the box itself. Okay, because particles cannot go outside the box, right? They are confined to the box only. So what is the maximum uncertainty in their position? That is L. Now the question is, uncertainty in the electron is more than that of momentum. Uncertainty in the momentum of the electron is more than that of proton. Uncertainty in the momentum of the proton is more than that of the electron, or uncertainty in the momenta of both electron and proton will be same, or we cannot tell without any information. This is one popular question at 10 plus 2 level. Okay, right? Now what is that? I want to apply uncertainty principle. So what do I do now? Okay, what does uncertainty principle say? Delta x into delta px greater than or equal to h bar by 2. Okay, greater than or equal to h bar by 2. So I'll write this formula here. Delta x into delta px greater than or equal to h bar by 2. So he is asking about uncertainties in momentum. Delta px greater than or equal to h bar by 2 into, right, delta x. Okay, when delta x is maximum, right, delta px will be minimum. What is the minimum uncertainty in the momentum? H bar by 2 into delta x maximum. What is delta x maximum? Both particles are present inside the same box. No, so uncertainty in their position for both of them will be L only. Okay, means delta x maximum is same. When delta x maximum is same, h bar by 2 is anyway constant. So what about delta px? Delta px will be same for both. Means uncertainty in their momenta, right, will be same for both the particles. Means electron and momentum uncertainty for electron, momentum uncertainty for the proton will be same. Okay, instead of uncertainty in momentum, if we ask uncertainty in velocity, okay, whose velocity can be found more accurately, whose velocity can be found with less accurately? If he asks that, I have to split this, what you call formula, delta px, right? I'll write it as what is p? P equal to mv. So delta p will be, right, m is anyway constant, m into delta v. My error will be in finding the velocity of the particle. So wherever delta p is there, I'll write it as m delta v. So that m delta v, if he asks uncertainty in velocity, what will happen, right? If he asks about uncertainty in velocity, right, I'll write delta px as what? Delta px as, right, m into delta vx greater than or equal to h bar by 2 into, right, delta x. I'll write. So delta vx equal to uncertain velocity. If the question is about velocity, I'll write like this: 2 into delta x into m. I'll write now. Okay, h bar by 2 is anyway constant, delta x is same for both. Okay, but m, whichever particle has more mass, uncertainty in velocity will be less. Whichever particle has less mass, uncertainty in its velocity will be more. Okay, means out of electron and proton, proton's mass is more. Okay, 1836 times more than that of electron. Means, right, uncertainty in the velocity of the proton will be lesser than that of electron. Means I can find proton's momentum more accurately than electron's velocity. What about momenta? Momenta for both particles is same because delta x is same. Okay, this is one simple conceptual question, one beautiful question which comes conceptual. It makes us to understand what is the uncertainty. If some particle is bound to some region, maximum uncertain position is the width of the region only. Electron is present inside the atom, but I don't know inside the atom where it is. Okay, but I can tell one thing: electron can be present anywhere from this end of the atom to this end of the atom. Means diameter of the atom itself becomes the maximum uncertainty for the position of the electron. Only thing I don't know is whether it is here or here or here or here. I cannot tell, but electron will be surely found inside the atom. Means diameter of the atom becomes the maximum uncertainty in the position of the electron. Similarly, a particle is present inside the nucleus. Okay, what you call the radius of the nucleus? Radius of the nucleus is about 10 to the power minus 15 meters, femtometers or Fermi we call. Okay, if I say, suppose I say that electron is present inside the nucleus. Okay, means inside the nucleus electron is present, but I cannot tell where exactly inside the nucleus electron is present. Electron can be present on this side, this end of the nucleus, or this end of the nucleus. Means from here to here it can stay anywhere. Okay, from here to here, it can stay anywhere. I cannot tell. I know only that electron is present inside the nucleus. So what is the maximum uncertainty in its position? Diameter of the nucleus itself. That I'll substitute in, right, in the uncertainty principle. So I'll write like this. Okay, delta px is greater than or equal to, I'll take the worst value only. So let us not take the other values. The minimum value is equal to h bar by 2 into delta x. What is delta x? Uncertainty in the position of the electron. Uncertainty in the position of the electron is how much? What is the minimum value of uncertainty? Equal to diameter of the nucleus. Diameter of the nucleus is of the order of 10 to the power minus 14 minus 15 meters. So I'll take 10 to the power minus 14 meters only. So h bar by 2 into 10 to the power minus 14. Okay, this is the minimum uncertainty in the momentum of the electron. Uncertainty in momentum itself is this much, right? Momentum should, worst value of momentum should be equal to this. As I told you, uncertainty in my height is 2 feet, means my minimum height should be 2 feet. No, anything more than 2 feet is acceptable, well and good. Okay, uncertainty momentum itself is coming out to be, it is like L plus delta L. Okay, delta L itself is this much, means L should, worst value of L should be equal to this much, worst value of momentum should be equal to this much, isn't it? Okay, so I'll take that worst value. Actually I can take the momentum is 100 times more than this value acceptable. Actually that's more logically correct, but still worst value I am taking. What is that? Momentum of the particle is equal to its uncertainty, means I am taking the worst value, delta L equal to delta L. Okay, means I'll take momentum itself as equal to this much. So I'll take px, I am taking the lowest value for momentum, that is equal to h bar by 2 into 10 to the power minus 14. If the minimum value of momentum is this much, what will be its kinetic energy? Kinetic energy equal to p square by 2m. That is, right, h bar square, h by 2 into 10 to the power minus 14 whole square by 2 into mass of the electron 9.1 into 10 to the power minus 31 kg. I'll substitute. I'll get the energy in joules. Okay, I'll convert that into electron volts. I'll be getting something around 1000 MeV. Okay, this 1000 MeV is the worst value for the energy an electron can have. Means if electron stays inside the nucleus, its lowest energy should be 1000 MeV. That is a conclusion given by Heisenberg's uncertainty principle. But what people have observed is, the most energetic electron coming out of the nucleus is nothing but beta decay. The most energetic electron coming out of the nucleus till now is found to have maximum energy of about 4.4 MeV only. Okay, but according to uncertainty principle, if electron is present inside the nucleus, its minimum value should be 1000 MeV. But till now, nobody has found any electron coming out with, forget about 1000 MeV. No electron has come out with 100 MeV also till now. Okay, the maximum value is around 4-5 MeV only. Okay, means how to reduce this value? Have to reduce the 10 to the power minus 14. Mass of the electron I cannot change. H bar and 2 values are constant. Only thing that is in my hands is what? Okay, I can change this delta x value. If delta x is more than this value, instead of 10 to the power minus 14, if I take the uncertainty in the position of the electron as 10 to the power minus 10, substitute this formula, then I am getting around 4-5 MeV. Means what does that mean? Uncertainty in the position of the electron cannot be around 10 to the power minus 14. It should be around 10 to the power minus 10. Means it should be in angstroms only. It cannot be in Fermis. Okay, what does that mean? It is impossible for the electron to stay inside the nucleus. Okay, but electron can present anywhere inside the atom. What is atomic diameter? Atomic diameters are in 10 to the power minus 10 meters. That is in angstroms. If you put delta x in angstroms, that acceptable values for the electron's energy are coming. Okay, but if you put in femtometers, okay, the size of the nucleus, impossible values are coming. So what does this proves? That it is impossible for the electron to stay inside the nucleus, but it can present anywhere inside the atom. Okay, that's how uncertainty principle has ruled out the presence of an electron inside the nucleus beyond doubt. Okay, right? Similar, but if I put mass of the proton, okay, m equal to, instead of electron, if I put the mass of the proton as 1.67 10 to the power minus 27 kg, then again meaningful values are coming. Means people are finding protons and neutrons and alpha particles with that energy if I substitute their masses. But electron mass, it cannot be nucleus. Means protons and neutrons can stay inside the nucleus. Electron can never stay inside the nucleus. It should be anywhere outside the nucleus only. Then if somebody immediately asks me, sir, how beta particles are coming out in beta decay from nucleus? So now I can confidently say that beta particle or electron is not existing inside the nucleus because uncertainty principle does not allow it. So what is happening? Something is happening. Electron is created there because it cannot stay inside the nucleus. The moment it is created, it gets thrown out. Okay, that's how we will approach beta decay. Whereas for an alpha particle, it is not like that. Alpha particle can exist inside the nucleus even before its emission. That is the essential difference between alpha decay and beta decay. That will be clear once we go into what is known as Gamow theory of alpha decay and Fermi's beta decay theories. Alpha particle can exist inside the nucleus even before its emission, but electron cannot stay. Beta particle cannot exist inside the nucleus before its emission. Just before the emission, a neutron transforms into a proton electron. Right, proton stays back, right, electron gets pushed out of the nucleus because it should not stay inside. Okay, that's how we approach those theories, right? So this is about the uncertainty principle. Significance of uncertainty principle: it has proved the non-existence of the electron inside the nucleus beyond doubt, we say. Now it has become an essential principle, as essential as conservation of energy. If somebody says I took 100 joules and I did 1000 joules, so far impossible, we say. Okay, similarly, if anything in nature is violating uncertainty principle, we can blindly say it is impossible. That phenomenon is not possible. Okay, so when somebody comes out to certain things, first people check whether it's according to uncertainty principle or not according to uncertainty principle. If it is not satisfying uncertainty principle, without looking into the details, we can say that process is not possible. Till now that is happening, people are successful with that. Okay, no violation of uncertainty principle has been observed. Now you may get a doubt. Okay, now I'll explain why electron cannot stay inside the nucleus in another way also. Every electron of mass m, okay, moving with some velocity v, will have some de Broglie wavelength given by lambda equal to h by p. The de Broglie wavelength of the electron is much bigger than the size of the nucleus. De Broglie wavelength of the electron will be in angstroms. Okay, whereas size of the nucleus is about femtometers Fermi. This is 10 to the power minus 15 meters, whereas this is 10 to the power minus 10 meters. Means size of the atom is, radius of the atom is about 1 lakh times bigger than the radius of the nucleus. Okay, right? So de Broglie wavelength of the electron is much bigger than the size of the nucleus. That's for new electron cannot stay inside nucleus. That way also you can answer. Or right, answer the electron cannot stay inside nucleus because if it has to stay inside nucleus, its energy should be worst value 1000 MeV. Okay, no electron is found to have that high energy. That is why it can be ruled out. Okay, it can be understood in 2 or 3 different ways also. Okay, this is about the uncertainty principle, okay, and its significance. Now we have seen about de Broglie concept, we have seen about Compton effect, photoelectric effect, and uncertainty principle. All these things come under wave particle duality. Wave particle duality in the syllabus for any JAM exam or in GATE exam or CSR in quantum mechanics, they'll give just one statement: wave particle duality, then Schrodinger wave equation, then etc etc etc. Okay, so that these 4 topics come under wave particle duality: photoelectric effect, Compton effect, de Broglie's concept, and uncertainty principle. Though uncertainty principle has come after the Schrodinger wave equation. After the Schrodinger wave equation, we studied it before. The uncertainty principle came at around 1928, I think, whereas quantum mechanics was developed in 1924, 1925. Means 3-4 years after that, uncertainty principle has come. But we study uncertainty principle before entering into Schrodinger wave equation, right? And things become easier. Okay, the sequence will be logical. Okay. So in the next video, we'll try to solve some problems starting from photoelectric effect up to uncertainty principle. After that, we'll go into Schrodinger wave equation, the actual wave mechanics or quantum mechanics. What are they? We'll see time independent Schrodinger equation. After that, what is physical significance of psi? What are the properties of psi? What are the postulates of quantum mechanics? And then we go into the applications of quantum mechanics. Okay, one by one. Thank you. I'll stop the video here.